Hello and welcome everyone to another video in our geometry concept series. And in this video, we are going to be starting to discuss theorems based on circles. So there's multiple different circle-based theorems that you might be aware of or might need to know in order to solve questions in your aptitude-based examinations, which are based on the topic of circles. So we'll go through these theorems one by one, and we'll see that how the theorems build up to each other. We'll also look at the derivation of these theorems, and I will talk briefly about the things that we have to be careful about when we are wanting to apply these theorems and in what kind of questions are they going to be relevant. So first theorem that I'm going to be talking about is probably the most famous theorem among circles, which is that the angle at the center is twice the angle at the circumference. Now, what this theorem essentially states is that if there are 2 points on the circumference, and if those 2 points are subtending an angle at the center, and the same 2 points are also subtending an angle at the circumference, an angle that they're subtending at the center will be 2 times of the angle that they're subtending at the circumference. For example, these 2 points A and B are subtending an angle of AOB at the center. They are subtending an angle ACB at the circumference. So angle AOB will be twice the measure of angle ACB. Let's try to prove this. So for the proof of this theorem, what I'm going to do is I'm going to first make a very simple construction. We make the construction in a different color. So what I'm going to do is I'm going to join O and C. So when I'm joining O and C, what is happening is I get the formation of 2 triangles, triangle AOC and triangle BOC, where O is the center of the circle. And in these 2 triangles, I can clearly say that AO and OC are equal. Similarly, OB and OC are also equal because all these 3 are radius of the circles, which means that each of triangles AOC and triangle BOC are isosceles triangles. So which means the base angles have to be equal. So that means that if I take angle OAC as x degrees, then angle OCA will also be equal to x degrees. And with the same logic, if angle OCB is y degrees, angle OBC will also be equal to y degrees. Excuse me. What this means is that angle AOC will be equal to 180 minus 2x. And angle BOC will be equal to 180 minus 2y. Because sum of all 3 angles of a triangle is 180 degrees. Now, if I add these 2 up, then on the left-hand side, I'll get angle AOC plus angle BOC, which in this case is angle AOB. It is the reflex of angle AOB, right? That angle AOB will be equal to 360 minus 2x minus 2y. So, which means that the non-reflex part of angle AOB, which means the other part of angle AOB on the other side of the center of the circle, will be 360 minus this. So the angle at the center, we write it as such, angle at the center will be 360 minus this angle. So 360 minus 2x minus 2y, which will give me angle at the center as 2x plus 2y, or simply 2 times of x plus y. And if you look at the angle at the circumference, the angle at the circumference, which is angle ACB, is x plus y. We write this better, that is x plus y. And this is why angle at the center is 2 times the angle at the circumference. Angle AOB will be twice of angle ACB. Now, if this proof is clear, let me just remove this proof. Hope this is absolutely clear and you made a note of it. Then let me explain things that you have to be careful about when we're applying this theorem. So let's say that I have a circle like this, and once again, the center of the circle, let me take it as O. And once again, let me take points A and B here. But this time, suppose A and B are subtending an angle at the circumference on the opposite side of the center. That they are subtending the angles at this point, C. So angle ACB, this angle ACB becomes the angle at the circumference. Now, which angle at the center is twice of this angle? So to find that out, what we have to be absolutely clear about is that the angle at the center needs to be measured in a different sector as compared to the angle at the circumference. So this angle ACB lies in the sector below the center. So I will have to measure the angle at the center above the center. So which means that it is this angle AOB, which will be twice of angle ACB, which means if angle ACB is alpha, then reflex of angle AOB will be twice of alpha. So remember this, keep this in mind while you're applying this theorem, that the angle in the center and the angle in the circumference need to be measured in different sectors of the circle. Only then will this theorem hold true. as we have seen in the derivation of the theorem itself. Also, very, very popular, very, very important corollary of this theorem is that angle in a semicircle is a right angle. So why angle in a semicircle? Because if, let's say, I take these 2 points A and B on the circumference, which are subtending an angle at the center and circumference as diametrically opposite points, which means that if I join OA and OB, then AB forms the diameter of the circle. Then the angle at the center that A and B are subtending is a straight angle which is equal to 180 degrees. And we know that a diameter divides a circle into two equal halves or into two semicircles. So any angle that is being subtended in the entire semicircle, any angle that is being subtended by the diameter in the entirety of the semicircle, like in this case, angle ACB, will be half of 180, which will be equal to 90. So angle in a semicircle is a right angle. So all these three come within the purview of the same circle theorems. Remember, as soon as you see two radii meeting at the center, and if it's an angle-based question in circles, most likely it is the application of this theorem. Also, if you see a semicircle in a question, then this corollary should immediately strike you as a very plausible concept to apply. Because right angles are very valuable resources in geometry. Why are they valuable? Why are they so valuable to solve geometry questions? Is because right angles give us a value of an angle, sure. But they also give us a right angle triangle. And in right angle triangles, you can apply the Pythagoras theorem, applying which you can find out lengths of certain lines and sides. Also, all trigonometric ratios are also defined for right angle triangles. So it doesn't matter whether the question is an angle-based question or a side-based question or a ratio-based question. Right angles are versatile. They can be used in any type of geometry questions. So wherever you find the opportunity to form a right angle, you should form the right angle and then see whether it can be applied in the solution of the question or not. And that is why when you look at a semicircle, immediately remembering that angle in a semicircle is a right angle is very important. All right, that's all for this video. Thank you.